This is a video production of the Ocean Mapping Group at the University of New Brunswick with the following participants. Colin Ware, a faculty member in the Faculty of Computer Science at UNB, was in charge of this project. Dave Fellows, another faculty member in the Faculty of Computer Science, was in charge of the systems aspects of the project. David Wells, a faculty member in the Surveying Engineering Department at UNB, is in charge of the hydrographic aspects of the project. Ken Doucette, a research assistant attached to the Ocean Mapping Group, was in charge of the data management aspects of the project. And Wing Wong, a graduate student in the Faculty of Computer Science, was in charge of the graphical editing tools associated with the project. You gotta get the, okay.
Hi, my name's Colin Ware. This videotape accompanies a report which is entitled Feasibility Study on the Use of Algorithms for Automatic Error Detection in Data from the FCG Smith. In that report, and in this videotape, we address 5 main objectives. The first objective is to assess the present methods for data processing on board the FCG Smith. Second objective is to address the feasibility of automatic classification of data points. The third objective is to show you some interactive editing tools which use algorithms to enhance their capability. And in fact, the main goal of this videotape is really to illustrate those automatic editing tools. The fourth objective is to assess the algorithms, or give you a summary of the results from algorithm assessment, both using statistics and using the help of a hydrographer to see how well the algorithms worked in conjunction with the interactive editing tools. And finally, we'll make some remarks about practical implementations, how we can migrate this prototype into a real working system on board ship. System on board the Smith is a Navitronic CDIG-21. The aspect of data processing which we want to concentrate on is that of removing blunders or data outliers which are caused by such things as fish, kelp, and air bubbles. At present, an integral part to this cleaning process is a field sheet chart, such as the one shown here, which contains, well, this one contains approximately 10,000 plotted data points, which are a subset of the raw data. This represents about 10% of the data which was available to the data processing system. It's actually less than 1% of the data which is actually acquired by the Navitronics. In the present system, a hydrographer will spend about a day poring over this sheet, looking at every single one of these 10,000 points and looking for anomalous points, that is, points which differ significantly from the surrounding data points. These the hydrographer marks with a pencil, and once the whole thing's been covered, the sheet is moved to a digitizing tablet, and that allows access to the computer, and it's possible then to get a table of the surrounding data points, and the hydrographer can decide whether that point is in fact anomalous and can be attributed to kelp, etc., and therefore deleted. At present, this process takes approximately 1 day for one pass over 1 day's data. And in the routine data cleaning process, this method is repeated 5 times on 5 different days. Actually, it's a minimum of 5 times. It may be more. Thus, it takes at least 5 days' data to clean 1 day's data acquisition, or to clean the data acquired on 1 day's surveying. This diagram shows the major components of the data cleaning system which we've implemented. In the first stage, the input file is partitioned using a partitioning tool which allows us to take standard size subsets from the original survey. In the next stage, an automatic classification algorithm is used, which we'll describe later, which basically looks for outliers with different levels of confidence. In the next stage, well, there's an optional interactive editing stage where the hydrographer can look at the data and confirm the decisions the algorithm has previously made, or if you like, change them. Finally, we have also done work in the last boxes at the bottom of this chart on assessing algorithms by comparing the results from applying algorithms to the data and with the results which are obtained from looking at the data which a hydrographer has cleaned. So we can make direct comparisons between hydrographer clean data and algorithm clean data. Okay, this tool allows us to form fixed size subsets of the data. This box here represents a square which is 250 meters on a side, and I can rotate this thing and place it in order to partition the data into a number of different subsets. I'll then type in a name for the subset, call it box 1. Click on Save Bounding Box, and I now have that subset, and as you can see, the highlighting tells me I've got it. Usually one overlapping subset, so I'll create another one here. Box 2. Whoops. Save that one. And so on. 3. So this Lewisburg survey, which has approximately 120,000 soundings in it, can be captured by a total of 6 boxes. We looked at 3 different options for automatic classification of data, and they had somewhat different purposes. The first option is to look at data classified into 2 classes, good and bad. This is fully automatic classification. That is, the algorithm simply decides whether a data point should be rejected or not. The second option, we thought that it would be useful to divide the data into 3 classes, good, definitely bad, and doubtful, with the idea that the hydrographer would only look at the doubtful data points. But once we'd worked with this idea for a while, we came to understand that in fact the hydrographer would much prefer to have a number of different levels of, in quotes, badness. That is, these are statistical measures of how far an outlier is from the statistical surface. And then the hydrographer can use this level information to make its decisions. So we ended up with, well, we've written n classes here, but as a practical matter, we decided on 8 different levels of badness. Level 0 being good, level 7 being very bad. To run. I'm now running the pre-processing algorithm on the data in box 4. This pre-processing algorithm makes heavy use of a device called a TAC1 application accelerator, although it could equally be done in a more conventional machine. What you're actually looking at now are floating point numbers being accumulated in various fields of the TAC image data memory. And what we're computing here is a digital approximation to the surface for the data in box 4, and a digital approximation, a digital continuous approximation to the standard deviation, the depth standard deviation information in that box. Once these digital models are created, which will be done shortly, we'll run through the data again, and then we'll test each data point against this surface, and as a function of the constant offsets from the data, that is, if, for example, a data point is more than 2 decimeters above the digital surface and more than, say, half a standard deviation above it, then flag it at one of the 8 levels which have been predefined. So now we're still seeing the computation of the digital models. That's just finished, and now we're dividing whole areas by other areas to create the digital terrain model and the digital standard deviation model. Okay, now the pre-flagging of data is occurring. At which the data is being flagged at any one of the 8 levels described previously. Done. That's because there's a whole track which is miles off. They're all actually zeros. We'll see that later. And they won't. The interactive editing tool has 4 windows. The first displays the track plot and standard deviation information. The second window, which we call the zoom window, contains a magnified portion of the first, part of the first. The other 2 are control panels, one of which controls view parameters, the size of the window you want to magnify, and so on, the ability to control which flags you look at in the data. And the final window is controlling the editing process. The editing tool, which has the digital standard deviation data already loaded, it's colored green now instead of blue, but otherwise it's exactly the same. You can see the ship's track plot for this region of the survey being plotted, and now the data is fully loaded. Now I'll put up the editing tool display panel, control panel, and the edit panel. So now we have the 4 windows displayed: the track plot window, the zoom window, the viewing control panel, and the editing control panel. And I just want to quickly show you some of the way these panels interact. Right now I'm moving a window here. It may be hard to see, but it's right here, which is the zoom window, and that's displaying, and over here you get the magnified data in the zoom window. I'll change the size of the data points there so that you can see them more easily. There are the data points within this zoom window. I can vary the size and shape of the zoom window. So now it's a long elongated box. I can also look at the data within this elongated box from the south instead of from above. So now you're seeing a view from the south, which shows you that this data corresponds to a gradient. I can also put up a scale here. The data here goes between 0 and 16 meters in depth. Let me just quickly show you some more functionality. I can show you, I don't know if there are any flags been set, but I can show flag data points. Okay, the points that are flashing in this window here, I'm not sure, yeah, I guess you can see them on the video, are in fact point soundings now which have had flag bit 3 previously set, flag bit 3 being bad navigation. Now I want to talk about each window in turn and describe its capabilities. Here we have the variable sized window, which is a kind of magnifying glass. We have the standard deviation information, and if you look at this you can immediately see there's a whole band of high standard deviation, and that in fact corresponds to an entire track, which you can see over here, which has depths of 0. So that's why we've got a high standard deviation down in this band, is because obviously something wasn't functioning and all the depths there are 0. You can see the track plot here, and you can see the standard deviation information. Over in this zoom window here, we can look at, well, let me first change the shape of this panel. I'm going to make it square just to illustrate a point. We have 3 different views in the zoom window here. we have the possibility of a plan view. What you're seeing now is a plan view of every sounding within the zoom window. These are color-coded according to ship's track. So you can see there are, in fact, you may not be able to distinguish all these colors, but I can. And there's a red track, there's a green track, and a blue track here, showing that in fact the ship passed over this area 3 times. You can see the flashing data, which means that the bad navigation bit was set for that particular set of 33 soundings. Okay, now we're looking at the top view now. I can also look at the south viewpoint. So this is a view of the same data from the south, and now this depth scale is meaningful, 0 to 16 meters. And I can look at the same data from the west. Now when you look at the data from the south or west, you generally don't want a square window, you want an elongated window. So I'm going to elongate the window and narrow it down. So now I have a window, well, now I have a window which is in fact only 2.5 meters thick and probably about 150 meters wide. So this is 150 meters and you're seeing the data in a narrow sort of slice, 2.5 meters thick. And now you can see a number of things here. You can see that in fact these red points here only came from a single pass of the ship, which suggests there's something wrong there. And in fact there's a few things wrong here. These green soundings here are also differ from the other passes of the ship. Okay, one of the things we implemented to allow people to look systematically at the data, what I've been showing you before is I can just use the mouse to move this window around freely, but I can also use step keys up in this region here to step up, down, or sideways through the data. So I can just click on this, and that allows me to step through the data by a fixed amount, 2.5 meters. And this is very useful if you want to systematically cover the survey region and make sure that you've hit every part of it. So now I'm clicking through that. Okay, let's go look at some other regions. I see over here there's a region with a high standard deviation. So let's go look at that one. I'll grab my viewing window, move it up there, and now you can see, maybe I'll make it a little wider so that we can make sure we've got everything. That actually has been, this high standard deviation has actually been caused by a couple of points up here, and those couple of points, since they're extreme outliers, have pulled up the surface, the standard deviation surface in that particular position. I'm going to narrow down the window now and show you the operation of the pre-flagging. The thing that's flashing here now is still just bad navigation bit. Now there are some outliers in here as well. There's a couple of outlying points down here and here, which about say I would guess from the scale they're about 0.4 decimeters above the surrounding points. Now let me show you the results of pre-flagging. So I'll set this on, pre-flagging on. Okay, we can vary the confidence match, as we've called it, for the pre-flagging, and that hits this point, that gets this point, it doesn't quite get that. I've got level 6 set. Level 7 actually gets even fewer points. We can go down. Okay, now as I get down to level 4, we are grabbing more of those points. Now we can get this point, this point, and this point. There's actually a number of points, and that's actually a little cluster of points there. Level 4, well, on level 3 now. Level 4 was actually the level at which the visiting hydrographer Mike Ruxton chose to operate. Okay, let me go now into just to quickly describe the editing mode. I have another window in this. I'll make it a bit bigger. This is an editing window. The use of this window is now to allow the operator to delete several data points at a time. What I can do now is I can set or I can confirm errors within this window, and basically the operation of this is set an operator flag bit for every point within this window which is flashing. The importance of this is that it allows an operator to flag many data points simultaneously. So I can get all the data points in there which are outliers. in one operation. So I can just click on the set flag and that's done. And in fact, if we now turn off the other flags and just look at flag bit 7, we can see that those bits have been set here. I should also turn off bit 3, and so within the window, the only bits flashing now are the operator flag bits. So in this way, I can set some confidence level that seems appropriate for the data given the particular survey conditions, level 3 perhaps, and then I can systematically move through the data and I can set flags at a particular level of confidence. Just here's another example. These soundings here, let's turn the flashing off and see what we can see. One of the things the hydrographer often wants to look at is to see whether the outlying data points come from a single pass of the ship or not, and you can tell that by the different color coding. So in fact, each of these outliers actually came from different passes, and so the hydrographer might very well wish to delete these. One final function we put in here is the ability to capture all the soundings within this box and print out the dataset number, which allows the hydrographer then to consult the sounding rolls and find the data from the Navitronics system. That is the high volume data, which at present doesn't get into the processing system. And this information is at present only available in sounding rolls, and so we provided that as a hook into the existing system. Here's another feature in the data, anomaly in the data, which we've discovered using these graphical tools, which we don't believe it would have been possible to have found using the previous tools. In this region here, well, it's this region here, enlarged over here, you can see this pink set of soundings are a mismatch with the other passes of the data over that region. And in fact, it's as if the ship were heeled over to the side in this particular region. And that, if I click through that region, you can see that those soundings continue for quite a distance. And there's a good chance that in this case, the hydrographer might ask for the ship to run over that area again, and in fact delete this whole set of soundings over some considerable distance, maybe 100 meters. They might want to completely delete that entire track. We use two methods to assess the effectiveness of these algorithms and procedures. The first is statistical. In the statistical processing, what we did was create the equivalent of a field sheet. That is, we used a thinning and shoal biasing algorithm to create a subset of the data based either on the operator flag data points or on the algorithm flag data points. Then, for each point within the operator clean set, we looked for the nearest neighbor and compiled statistics on depth differences for nearest neighbor. Just to give you an example, on one comparison, out of a total of 2,836 soundings of operator flagged thin data, there were 31 soundings where the algorithm flag data differed by more than 2 decimeters from the operator thin data. There were 204 soundings which differed by more than 1 decimeter. To put this another way, 93% of the soundings are within 1 decimeter of the operator flag data, and 99% of the soundings are within 2 decimeters of the operator flag data. Now, we concluded from this and from the various comments of the hydrographers relating to safety that it is not feasible at the present time to have purely algorithmic cleaning of the data. There are simply too many risks to navigation involved, and there's the possibility that outliers which are removed by the algorithm might in fact be navigation hazards. So We also, as you've seen, incorporated the algorithms into a kind of power-assisted editing approach, and we evaluated this with the assistance of a CHS hydrographer, Mike Gluckston, who made 2 visits to UNB and worked with these tools in cleaning data. On his second visit, he was actually able to clean a sample of the data from a 1988 Calicut survey. It took him approximately an hour and a half to clean 1/14 of one day's data. Now, that was the first try, and we believe that you could easily double the productivity as an operator, as a hydrographer became more experienced with these. And so our conclusion from this is that at least it seems reasonable that it should be possible to clean one day's data in one day using these prototype tools, or at least an improved version of these prototype tools. There may also be things gained, and undoubtedly there will be time gains, efficiency gains from improvements on these tools, because these are very much prototypes that you've seen here.
This has been a production of the Ocean Mapping Group at the University of New Brunswick in Fredericton, New Brunswick, Canada. Video production of the Ocean Mapping Group at the University of New Brunswick in Fredericton, New Brunswick, Canada. Hi, I'm Dave Wells. I'm a member of the Ocean Mapping Group at the University of New Brunswick, and we prepared this videotape to describe some of the tools that we've developed under a strategic grant awarded to us in November 1988 by the Natural Sciences and Engineering Research Council of Canada. During the first 6 months of this grant, that is the first half of 1989, we became familiar with the data coming from 3 high-density bathymetric data acquisition systems, the Navitronic Sweep system, the Simrad EM100 multi-beam swath system, and the Larsen 500 airborne LiDAR system. We defined the data structures that we would use to accept data from these and other systems, and we purchased and installed 3 Sun 4 workstations, which became operational in May of 1989. We also identified 3 steps required in the cleaning of the data from these high-density data sets. And these are to check, first of all, whether the navigation is okay, and if not, to correct it. Secondly, to check whether all of the depth data points are okay, and in general they will not be. So we have to identify and flag the bad data points. And thirdly, to check whether overlapping data is consistent, and if not, make further corrections. The strategy that we've developed for building our data cleaning tools for high volume bathymetric data is shown on this list here. In general, we would do automatic cleaning as appropriate, and then use manual tools to check and refine what the automatic cleaning tools have done. In this case, the automatic assessment would be whether the data points are good, bad, or questionable, and we would manually assess only the questionable points. Eventually, we would expect that all of the tools would be managed under an expert systems shell, which allows convenient rule modification and a shift to greater automation as the knowledge base warrants it. The first thing that you'll be seeing on this videotape is a number of viewing tools that have been developed over the last 6 months, and we've emphasized the development of viewing tools for a number of reasons. First of all, we will require using these viewing tools to understand the features in the data that we will require having automatic tools to process. Secondly, we'll want to use the manual viewing tools to check the performance of the automatic tools that we'll be developing. And thirdly, In production cleaning of bathymetry, it will be necessary to refine and check the performance of the automatic tools, and these manual viewing tools will be used for that. To look at the manual viewing tools that you will be seeing, they are shown here. There are 6 viewing tools. The ones that are shaded, the 4 that are shaded, provide a final output for the operator to understand some features of the data. And these 2 unshaded tools here are used to control certain aspects of the view being shown. Okay. Following the description of the viewing tools, we'll look into some of the other tools that are being developed. Vector raster integration, neural networks, how the expert system shell can be used to manage the tools, and for the future, animation of the data by navigating in a 3-dimensional virtual environment. There are also tools in other areas being developed that are not included on this videotape, such as in interface to databases. A number of tools working on the Ocean Mapping Group's Sun 4 workstations. The test data that we'll be using to demonstrate these tools, for the most part, will be data that was given to us by the Bedford Institute, collected on board the Smith, the sweep vessel, the Smith, in August of 1989 in Louisburg off Cape Breton. What we're showing you now is the boat board that was created on board the Smith. The tool that is used on board the Smith at the present time to check whether or not triple coverage was obtained presents the output that we see in this plot, which was all of the plots that were obtained from the processing on board the Smith, and it is a version of the section of the field sheet for this survey. Creation of this plot is the major bottleneck in the present processing on board the Smith. It's an iterative process. This plot is first created and then manually examined for bad depths. Those bad depths are then removed in a rather inconvenient way from the data file, and the process repeated. When you do that.
Yep. Hello, I'm Wing Wong. I'm a computer science graduate student here at the University of New Brunswick. I'm with the Ocean Mapping Group here, and my work deals with 2-dimensional visualization of swath data. I've developed a set of tools which I'll demonstrate shortly that allows interactive manipulation and visualization of such data. Let's go to the lab now. Let's go. This is a tool that I've developed. It's called the Interactive Swath Viewer. It's consisting of 3 basic components. To the right here, we have an abbreviated version of the ship's track plot, and the user can select a region of the track plot that can be blown up to be displayed in the window here. The size of the user's selected region, as well as other attributes, can be set using this control panel right here. Region of the track plot to be displayed using a window that is controlled by the mouse. And the size of the window can be adjusted using the control panel to look at either a larger or a smaller area. Okay, let's move the window down here. And you see that in this area we have an expanded view of the region that we selected using the window. Each of those points represent a sounding, and the system at the moment can accommodate approximately 1.5 million of those soundings. You also see that each sounding is color-coded by height, and this is the color sequence that we use in these demonstrations to highlight the depth. A different color sequence can be loaded, and the size of each reading can be adjusted using another slider bar in the control panel, so that we can accommodate different density of data. For instance, we can make it bigger. There are some flashing points in the data display area. This is because the Canadian Hydrographic Services has defined 8 flag bits to be associated with each data point to indicate various types of conditions in the data. And with this tool, we can interactively specify a bit pattern that we can use to highlight certain aspects of the data. For instance, right now we are looking at the points with bit number 3 and bit number 4 set. And we can, let's say, turn off bit number 3 to look at only those points with bit number 4 set. And bit number 4 indicates bad data points. And we can look at those points with bit number 3 set, and bit number 3 indicates navigation error. Okay. In addition to being able to look at the data from the top, we also have the option of looking at the data, the elevation data from the south by clicking on this button over here. This may enable us to pinpoint outliers easier. This tool at this moment is only able to visualize the data, but later versions of this tool will incorporate editing capabilities as well. This is a tool that I implemented on a Sun computer called a color sequence editor. What we're trying to do here is to do 8-bit colorization of a file format called the IFF, or the image file format. And we have an IFF file loaded in this part of the display, and we'll map each pixel in this map onto a color sequence here that we can create, that we can edit, and that we can save. The color sequence is sometimes called a color map, or sometimes called a color lookup table, and is used by many other tools that we've developed as well. In this tool, we use the HSV color model, which stands for hue, saturation, and value or brightness. This is the hue spectrum, which approximates the color spectrum. This is the saturation, and this is the value. And we can adjust the color sequence by drawing lines in the various boxes. For instance, we can adjust the brightness like this to bring out specific features of the image. Or we can create a different spectrum. And the resulting color sequence can then be saved as a file.
Okay, what this tool does is it loads an image file and it impoverishes it. That is, it selects a small subset of it so that we can move around and define a view. The essential purpose of this tool is to define a perspective view of a set of data. At the moment I've got tilt spin set, so I can turn it around, I can tilt it, I can also change how extreme the perspective is. And there's a reasonable view. And do all the basic operations. I can move it up and down, sideways, zoom. Using this tool you can also specify the illumination of the surface. And illumination is changed simply by moving the mouse left and right, which allows us to move the position of the source to the north and to the west, to the east, wherever desired. Feedback for the illumination position is given in 3 different ways with 3 different boxes. This box here shows the shadow as a compass, so illumination is given effectively by the extent of the shadow. Feedback is also given by this, which shows the shadow angle directly. Finally, feedback is also given here by a kind of perspective view, which shows a shadow. And of course, the feedback is also given by the view of the surface, where you can directly see on this sketchy view of the surface how the illumination is going to look. Other attributes of the illumination that you can change are the ratio of the ambient light to the focal light. Ambient is simply the amount of light from the surrounding, and it's modeled by a constant here. You can also change the amount of specular illumination, which is essentially making the surface look glossy. If you have high specular, it'll be a glossy surface. Low specular, it'll look like a matte surface. We can also, if we want, have cast shadows, and we can, if we desire to have cast shadows, we can vary the fuzziness of the shadows. So in a sense, what you're modeling there is the extent of the light source. Okay, this is to illustrate a second application of the TAC, in this case to measure the coverage obtained in survey. This uses other primitive operations which are supported by the TAC. In this case, we're doing a lot of a lot of ORs, a lot of digital ORs between data that's read in. Let me show you the low region of the TAC first. The TAC can be considered as divided into regions A and B. And this is region B. What you're seeing here is 1,000 data points, another 1,000 data points, another 1,000 data points. A circle is drawn around each of these data points, and they are ORed into the frame buffer. So each circle has a value 1, 0 is outside. All these are ORed together, so you just get an estimate of the coverage for that 1,000 data points. Okay, these little strips of 1,000 data points are subsequently summed into the top region of the TAC, which you see here. So here you see 1,000 data points at a time, as generated in the bottom region, being summed up into here. And this gives us a way of quite nicely visualizing the coverage. So in this, with this color here, you can see there was a single, this area has been covered once, this area here has been covered twice, and the areas which look white have been covered 3 times.
Okay.
My name is Colin Ware. I'm a computer scientist at UNB and also a member of the Ocean Mapping Group. The algorithms I'm going to describe have been developed with William Knight, who's a statistician at UNB. These algorithms have essentially 3 purposes. The first is to derive statistical surfaces given random data. By random, I mean not regularly gridded data. The second purpose, well, these surfaces are statistical in the sense that 1, they approximate the ocean floor. 2, from these we can also derive measures such as standard deviations. And 3, we can also derive measures of coverage, how many times the ship's passed over a particular area when it's doing a swath survey. The second goal is to explore the potential of a particular piece of hardware that we bought called the TAC Application Accelerator, which is on our Sun 4. And this hardware consists essentially of a large frame buffer, that's a large piece of image memory, together with onboard processors to allow you to do image processing kind of work very rapidly. And the third goal of this work is to apply these tools specifically to the problem of detecting outliers. That is, for detecting outlying points which might have been caused by, let's say, the presence of fish or air bubbles and do not in fact represent the ocean floor. To illustrate the way the TAC can be used and also to illustrate some of its computational power, I'm going to show you a fairly small example using approximately 4,000 data points. In this example, the TAC memory is divided into 5 different regions. 4 of them are visible, 1, 2, 3, 4, and there's a further one which is invisible further further down. And in these regions, weight fields are accumulated around each data point. In one of the regions you get weighted depths, in another region you get simply the sum of the weights, in yet another region you get sum of the weighted depths squared. What you were seeing just then was a subsequent stage of processing in which entire regions measuring 512 by 512 are divided by other entire regions. Now you saw how fast that happened, and in each of those events, which took a fraction of a second, there were in fact 250,000 floating point divisions occurring, or in some cases 250,000 floating point multiplies, which illustrates the particular strength of the tank, that it can do these operations which look like array processing. It's not in fact an array processor, but it has pipelining of operations which enable it to do very, very fast floating point computations on large arrays of data of this kind. The result here is that we have two representations of the data. One is a kind of running average of the depths, shallow here, deep here. The second one is a running standard deviation over the surface. So it's high standard deviation where it's blue and low standard deviation where it's black. In fact, the standard deviation data is also represented over here on top of the red-green scale. What you're seeing here is a perspective view of a digital terrain model, and the digital terrain model and its appearance are in fact the result of a number of the tools you've seen previously. The color sequence editor was used to specify the color of the surface. The color of the surface, in fact, is the product of a calculation to derive the standard deviation of the surface. So here, surface color represents standard deviation. The height was modeled, again, using that previous technique of generating a kind of running average of the surface. And the illumination was specified using the view specification tool that you saw previously. This digital terrain model, as you can see, takes a while to generate. It contains, let me see, it contains about 1 million triangles. So what you're seeing now is 1 million triangles being generated slowly and run through the perspective projection.
My name is Richard Pollock. I work at the Remote Sensing Lab at the Department of Survey and Engineering at the University of New Brunswick. I'm currently working on a project concerned with integrating raster image analysis and geographic information technology based on vector data. We've received a sum of money from the Ministry of Commerce and Technology in New Brunswick in order to develop combined raster image handling, vector data handling capability towards supporting local industry in this province. To that effect, we've taken an existing geographic information system produced in this province and have extended it with raster image handling capabilities. We've started off supporting visual analysis of the raster imagery by developing a combined raster vector display. It's totally integrated with the geographic information system so that all the existing functionality remains, and the new raster image handling functionality is truly an extension of what's there without having to switch from one system to another. At the moment, we're going beyond merely displaying that raster imagery, and they're working more towards automated understanding of that raster imagery using the geographic information system as a knowledge source. This will be applicable to the ocean mapping arena as well, because in that context there's data from different sources having different formats, some raster, some vector, that need to be treated in an integrated manner in the same way that we've done with terrestrial data.
So this is an aerial photograph and the same vector data that we just saw.
Yeah.
Okay.
The aerial photograph ends here. I mean, it's
Yes.
not too good, is it?
No, that's okay. All right. Now, there's misregistration, obviously.
If you need it.
Right.
So what I'll do is I'll rotate the vectors because, you know, this type of displacement suggests possible rotation to bring them into registration.
Okay.
So, rotation. Wrong direction. Now the map is being redrawn over and over again, but I can get rid of the old lines and just keep the new ones. Okay. Now perhaps I'd want to do a shift downwards, a translation downwards. Do that. So that's a better fit than what I had before. And I did a combination of a rotation, a skew, and translation in two directions. The aerial photography suggests that there's it shows a road going along here. Now after making the correction, I can now add in a line to represent that road. It ties to along the line that's evident on the raster imagery. Now what I'm going to do is I'm going to redraw the map without the correction. Okay. Now you see this line is no longer it's no longer in registration with the aerial photograph because it's in registration with the original uncorrected map.
Right.
So it's a practical way of getting around imperfections in overall image map registration.
Hi, my name is John Cardozo and I'm working with Brad Nickerson and Ocean Map with the Ocean Mapping Group. And we are trying to work particularly using artificial intelligence ideas and biologically inspired methods, in different ways to look at the data and identifying different problems. We are working mainly in peak detection and topographic feature detection. And I mean with that, I mean to be able to look to the data and identify areas of problems, for instance, in hills, valleys, ramps, features, problem features such as the omega, what do you call that, omega shapes and so on. So, we are going to talk about two different things. One is peak detection and the other one is feature detection. In peak detection we use a network-defined method of pre-hardwired weights to identify peaks in the data. In the feature detection, we use a backpropagation with two hidden layers neural network to learn about the features that we wanted to find and then we'll let it run in the testing mode to localize these features in the data. Again, perhaps? Okay, in the top window we have the drawing of one profile. Each point, 33 points, each point representing the depth at that particular point. The bottom curves, the top one represents the threshold, the bottom one represents the difference between one point and the bias of that point. When this difference is greater than the threshold, the point is a potential troublemaker, is probably a faulty data point, and then we'll examine it more carefully in a two-dimensional type of peak detection. But right now we are examining each point, individual points in a single profile. Topographic feature detection, it's implemented through a more or less known network. The backpropagation network is a multi-layer network with hidden layers, two hidden layers. Some feature by drawing a profile and storing this profile in some data file, and after having the network learning the feature that we have defined. Once the network learns that feature, we will we'll have to do something here now. Once the network learns that feature, the network is let what do you say? Is going to work on the data and try to localize areas in the data file where that feature exists, hopefully.
My name is Brad Nickerson. I'm with the School of Computer Science here at UNB, and I'm a member of the Ocean Mapping Group. One of the major driving forces for the adequate processing of this modern-day swath data is the simple amount of data that's involved. Upwards of 1 to 2 million points per day, which hopefully will be able to be determined on the ship a day later to be adequate or not. So there is a lot of decision making that needs to be taking place on board the ship by usually experienced hydrographers as to whether or not the data is adequate for their purposes. Paramount in their concerns is the fact that there may be a depth anomaly, and related to that fact, of course, is the fact that there may be some navigation errors or inconsistencies. In order to speed up the process and hopefully make the more tedious tasks less cumbersome, it would be advantageous to have tools, or to have a tool which would be able to make the same types of high-level decisions that the hydrographers would make. Part of my research interests are in artificial intelligence, in particular expert systems, and one aspect in the Ocean Mapping Group at which I'm investigating, is the use of an expert system approach for the integration of some of the lower level tools that you have seen discussed elsewhere. This is the development studio for the high-level expert system shell called ART. ART stands for Automated Reasoning Tool, and it's written in Lisp, and Lisp can in turn call any C program running on the Sun 4150. What I'm going to demonstrate here is a very simple example of using ART to call the viewer tool developed by Wing Wong, and then returning once again to the ART command window. illustrating that in fact the high-level shell art can drive the appropriate tools in a rule-based fashion depending on the contents of the swath data. So I'm going to actually start the example now by resetting the knowledge base. And then running the example. So I'm now invoking ARC with particular window size and location. And it in turn has invoked the viewer tool and is now reading the Lewisburg data into the right-hand window first of all, the track positions. And you notice quite clearly that the window has now been positioned according to my instructions at the high-level ART command level down in this lower right-hand corner. Here is manually changing the size of the pixels so that they show up well for the size of the window that has been chosen. We could have ART rules also size the pixels relative to the size of the window such that it's appropriate for the human viewer in some semi-optimal way. Now what you see here clearly is that there are about 6 depths in the center of this window that are anomalous. The orange and yellow colors are used to indicate very high points or low depths. Once we're finished with the viewer tool, we can then return to ART and pick up where we left off. In this case, there are no other rules applicable, so no other actions take place. Conceivably, we could actually then display another appropriately sized and placed window for the operator, or choose another tool based on a decision made in the viewer tool.
Rolling?
Yep.
Hi, I'm Colin Ware. What I'm going to describe is a project for manipulating and investigating and navigating in virtual 3D environments displayed on a high-performance graphics workstation. The hardware components of this project are, well, the most novel one is this device here, which we call a bat. It's like a mouse that flies. It knows where it is in terms of Y translation, X translation, and Z translation, and 3 dimensions of orientation, rotation in azimuth, elevation, and roll. The other primary component is the Silicon Graphics Iris workstation, which is capable of rendering 3D scenes and allowing us to move through them in real time. What we're going to show you is this device in 3 different interaction modes for manipulating scenes and navigating through the scenes. The 3 modes are, 1 we call scene in hand. That's as if you have the scene mounted on the device. When you move your hand towards you, the scene moves towards you. 2 is virtual flight simulator. In this case, it's not like a real flight simulator, but what we're actually controlling is velocities rather than positions. So as I move my hand forward, I start to move forward, my viewpoint starts to move forward. As I move left, my viewpoint starts to move left, so I'm changing velocities. And the same with rotation, so I introduce angular velocities as I rotate my hand. The third one is what we call eyeball in hand, in which you can imagine the scene laid out invisibly before you, And you can only look at it through the eyeball, which is in your hand, and you can move it around. It's as if, in fact, you had a small handy cam in your hand. You have the scene, but the only way you can actually see what the handy cam sees is by looking at the monitor. This is the scene-in-hand interaction metaphor. In this metaphor, the button on this device is used as a clutch, and to move the device left, the object left, I move my hand left, to move right, move my hand right, up, down, and also it's tied to rotation, so if I want to twist it, twist my hand, and so on. This interaction method works very well where you have a lot of discrete objects which can be independently moved around. It's probably enough. Simulation interaction metaphor where I control velocities. So to move forward, I move my hand forward, and that starts me off at a steady velocity going into the scene. I want to go up a little bit to correct here. I move my hand up. I want to go left a little bit, move my hand left. Continue into the scene. I'll continue down the hallway, turn around the corner just by twisting my hand. Let's go in and examine this thing. This allows fairly fine control, so I can move quite close to things and still have steadiness, which wasn't true with the last interaction metaphor. We just turn around now. We'll head out. Action metaphor has a number of nice properties. One, it produces very smooth motion. It's also very useful when you want to move through arbitrary data that you don't know anything about. But unlike the other metaphors, it's relatively hard to learn. It takes perhaps 20 minutes to be able to use it reasonably well, whereas the other ones are much easier to learn. However, once learned, it seems to be the preferred mode of interaction. Okay, the third interaction metaphor we call the eyeball-in-hand metaphor. Now it's as if you have a little handy cam in your hand, you have a model of the scene in front of you, and the only way you can see it is through this eyeball here, this viewpoint. So, if I want to move around, I move around like this. Oops, I just went below the floor. I want to move around the other way, I can move around like this. If I want to move in, I move my hand in, like this. I can move across to this guy. As you can see, there are problems in terms of steadiness. It's hard to hold my hand that steady, and it's very hard to get in very close and look at precise details. But it is a very easy to learn concepts, and people find it easy to use quickly. Where it really becomes a problem is when you turn around and look at the back of the scene, in which case the correspondence between my hand motion and what happens on the screen becomes opposite. People have a hard time handling that. Well, that was Let me describe what you're seeing in this image. First, you're seeing a digital terrain model, which is generated from the non-uniformly distributed data. So this is, you're seeing a regularly gridded map. And this allows you to get a very intuitive view of the surface. It's obviously quite clear that there's some sharp ridges here, valley here, etc. What you're seeing in the form of color, as opposed to height, is the standard deviation of the surface. Thus, for example, this point here, this is clearly a bump. It's colored yellow, red then yellow, which indicates high standard deviation. that high standard deviation and the bump was in fact caused by two outlying data points which pulled the surface up, and because they are anomalies, they give a high standard deviation. Standard deviation is also higher in this region because the data are widely scattered in depth. The soundings in this region, all over this region, are widely scattered in depth, I believe because of the presence of kelp beds here, which yield multiple echoes, both from the kelp and from the seabed. The uses of the digital terrain model and the standard deviation, at least our immediate use, is to obtain, one, an estimate of how good the data is, how accurate the soundings are. Standard deviation can tell you how reliable the data is. But in particular, we're working on algorithms for outlier detection. And outlier detection should be a function of noise in the data. That is, if the data is very, very consistent, as down here, something is an outlier if it's only a short distance above the surface, whereas where the data is inherently noisy here, an outlier presumably will require a higher threshold. That is, maybe half a meter here would be something you consider an outlier, or a meter, whereas here you might consider a data point to be an outlier if it's only 2 decimeters above the surrounding data points. So the kind of algorithm we're looking at for detecting outliers will consider an outlier as a function both of the surface in a particular region and the standard deviation of the data in that region. Where there are bands showing high standard deviation, there's a band around here and there's a strip along here. In this case, this is a high standard deviation which is probably attributable to an entire ship's track. That is, in one pass over the area, that particular pass deviates from the other two passes. Remember, there's triple coverage in this data, so one of the passes disagrees with the other two. And we're actually working on developing the algorithm so we can separate out standard deviation from due to essentially noisy data, if you will, as opposed to noise due to an entire pass being different from the other two passes. This shows the same digital terrain map with different data mapped in color onto it. In this case, what you're seeing mapped onto the digital terrain map is the coverage map, which you saw previously being generated, only it looks somewhat different because we've used a different color sequence to describe it. This color sequence only has two values, white and blue. White shows where there's only double coverage, and blue shows regions where there is triple or more coverage. And so you can, in this way, even more dramatically see where triple coverage has been achieved, and also you can very readily match regions of poor coverage or high coverage with the underlying terrain.